Hi, I'm Courtney Lamb, and along with April Taylor, we will be presenting this module on place value development. As we go through this module, you'll be asked to pause and think at times, and other times, a task or a video may pop up. Take these moments to do the task or watch the videos and reflect on your own. Your work will help with the assignments and reflection prompt for this module. In this module, we will look at place value concepts and how to develop these with children. We'll have the opportunity to watch student videos and experience tasks that will help develop place value understanding. Take a moment to identify where you think 1000 would fall on this number line. Go ahead and pause here if you need to. So, where did you place 1000? What strategy did you use? You may have used this strategy thinking, I divided 1 million by 10 to find 100,000. Then I divided 100,000 by 10 to locate 10,000. Next, I divided 10,000 by 10 to locate 1,000. You used your base 10 knowledge and equally divided a quantity by 10 each time to determine a smaller unit. Take a moment to look at this base 10 chart and think about what it shows and how it is potentially useful. Pause here if you need some think time. Numbers in our system grow by increasing powers of 10 as you go to the left and decreasing by powers of 10 as you go to the right. At the center of this chart is our base unit of 1. We often see place value charts where the decimal is seen as the balance point of the number system, but shifting the focus to the ones place, our base unit, instead helps us see symmetry across the number system and can help answer the question of why there aren't ones, which is a logical question if your focus is on the decimal point as the center. Instead, if we get to the unit, 1, and have to decrease by a power of 10, we end up dividing by 10 and thus have tenths. It's notable that in our normal number line, we increase to the right. Yet in how we write numbers, we start with the largest place value to the left. Students come to us with these conflicting conventions about place value and number lines, which may result in some misconceptions. We do not want to get rid of this chart or number lines, but simply want to have students see this is not a number line, but rather a tool for a specific purpose. Helps us to understand the way we write numbers. Throughout elementary school, students are developing an understanding of our base 10 system that will support them in working with larger numbers and understanding concepts like decimals and scientific notation as they move into middle school. These concepts connect directly to the ideas of iterating and partitioning. As we move up in place value, we are multiplying by 10 or iterating to the current value 10 times. This connects to the idea of powers of 10. So 100 can be thought of as 10 times 10 or 10 to the second power. Or 10,000 can be thought of as 10 times 10 times 10 times 10 or 10 to the fourth power. In thinking about the previous slide and the base 10 chart, our notational system combines the multiplicative relationship, 10 times the value of the unit to the right, with the positional system of where each place has a value. Young children have some knowledge of two-digit numbers. They can count up to 2 digits and identify the names of the digits, but place value development takes time. Students progress through different levels of understanding the concept of 10 and the idea of unitizing, which is composing units to make a new unit. In the first level, the initial concept of 10, a student does not see 10 as its own unit. There's no sense of grouping by a 10. 10 objects are 10 individual units of 1. For example, the number 34 means 34 ones, and the students do not separate the quantity into place value groups. If you see a child counting a large quantity by ones, this is his or her level of understanding. In the next level, the intermediate concept of 10, a student begins to see 10 as a unit, but still relies on models to compute when working with units of 10. A student will count bars of 10, saying 10, 20, 30, and so on. The idea that 10 ones makes 10 is a key shift in mathematical thinking and the beginning of understanding the powers of 10. A student with a facile concept of 10 can easily count and compute by tens without models. Traditionally, teachers have assumed students had a solid sense of place value understanding if they could identify the value of a digit or identify the names of the places and expand a number with standard notation. While these skills demonstrate some place value knowledge, they do not represent a deep conceptual understanding. Students can provide correct answers to these types of problems without a strong understanding of the base 10 number system. We are now going to do a series of tasks that press students' place value understanding to a deeper level. Look for the pop ups throughout the slides to do the tasks. As we discussed when looking at the problem types, context provides students the opportunity to do mathematics and productively struggle. Given a context, students can act upon and represent quantities and relationships as they develop a solution strategy. Pause here and choose one of these problems to solve without the use of the standard algorithm. In the next slide, watch a video of 7-year-old Brennan solve the problem 486 into boxes of 10.
10, 20, 30, 40, 50, 60, 70, 80, 90, 100. 2 times 10 and 4 times 10 would be 4 times 10 is 40. Now I have 60 more, so another 6. I have 46 right now. Then I get 8, and well, that makes it 47 because plus 1 more.
Click each pop-up to view the different videos. As you watch the different students, think about how the solution strategy reveals the understanding of the base 10 system. Also, refer back to slide 8 and think about where each child is developmentally. Does the child show an initial, intermediate, or facile concept of 10? Read each question and click on the button for the pop-up video. As you see in the videos, the students are able to solve the problems, yet the strategy each child uses is a window into their understanding. For example, the first student uses the bars of 10, but is not able to count each bar as 10. Once grouped, she goes back to count each cube to get 34. The fourth student demonstrates a strong sense of place value. Not only does she use mental math to solve the problem, but she articulates well the idea of 10 tens and 100 and 30 tens and 300. Imagine the student's ability to work with decimals and scientific notation in later grades.
Giving students tasks using models is another way to develop place value ideas. Models are powerful tools that allow students to physically manipulate and visualize the base 10 concept, thus deepening their understanding. They can construct and see 10 as both a single unit or as 10 units of 1. And they can see 100 as a single unit or as 10 units of 10 or even 100 units of 1. Asking students to show multiple ways to represent a number can reinforce these relationships between ones, tens, and hundreds. And then if we're using groupable models such as cubes, counters, popsicle sticks, straws, and beans, those are easy to group into units of 10. And it's important to use models students can group before moving to pre-grouped models such as base 10 blocks. So take a moment right now and find 5 ways that you could represent 125. So when students can decompose a number in non-standard way, this demonstrates a strong understanding of place value and equivalent relationships. The students understand that each digit represents a unit, but it could be partitioned into many different units and still be equal. For example, 125 is the same as 9 units of 10 and 35 units of 1. Think about how this is connected to flexible computation strategies. This is something we'll continue to discuss in our next module. We could also use the bar model to make connections between notation and the units 10 and 1. Pause here and consider these 3 questions. Pressing students to show how the model represents the digits in a numeral emphasizes the idea that the 3 is 3 units of 10 in 32 and 3 units of 1 in 23. Though both numbers use the same digit, the places of the digits signify different units, as we see in this bar model. Another representation we can use to develop place value concepts is the visual 100 grid. Take a moment, answer these questions by looking at the grid, and then review the answers on the next slide. Question 1. How many tiny squares are in the entire grid? How many tiny squares would represent 1/2 of the entire grid? If we had 5 of these grids, how many tiny squares would we have? What if we had 10? How many tiny squares would we have? And our challenge question, if the whole grid was worth 10, what would each square be worth? What would a row of squares be worth? This model helps us visualize powers of 10 and the concept of unitizing. With guidance, students can see each square iterated 10 times to create a row, and then each row iterated 10 times to create the whole grid. And we can see the multiplicative growth of 10. 1 times 10 times 10 is the same as 100. We can even iterate the grid 10 times to visually see 1,000. The challenge questions really target that idea of unitizing. If we change the value of the whole, what is the new value of each row or square? In developing these key ideas about place value, students are expected to make connections across many skills and concepts. We want to keep in mind the questions we pose to children, the activities we provide, and the language we use to describe these connections. Students must make meaning of the 10 makes 1 relationship. We can do this by asking students to connect their strategies to models and by calling attention to their groupings in their oral and written names. For example, given a grouping of 2 10s and 12 1s, and another grouping of 3 10s and 2 1s, what might be some questions that we could ask students? Maybe something like, are they equal? How do you know? How are the units in each grouping the same or different? How could we count these quantities? What number names do we use to represent each grouping? And what numerals do we use to represent each grouping? By working through these types of questions, students comprehend how digits, positional number names, and units give meaning to each other. As students become more confident about place value, we can start to ask questions that press them to think beyond the value of a specific digit and start to see relationships between the place values. Place value riddles do just that. For example, we might ask how many 10s are in a number, pressing beyond just 5 or 4 to think about how many full 10s there are represented within a whole number, similar to our candy problem. Take a moment here to solve these problems and then move on to the next slide to see the answers. Depending on age level, students might answer this problem in 1 of 2 different ways. Initially, we may just be thinking about full 10s, 5 full 10s, 24 full 10s, or 103 full 10s. But eventually, we'd want students to think about the unit 1 as 1/10 of 10. And thus, we can see how thinking about 3 as 3/10 of 10, making this answer 5 3/10 rather than just 5. The other riddles press students to make new units to find the total. Reflect back and compare these to the traditional place value questions presented earlier in the module. Problem strings are a series of related problems sequenced so that they highlight relationships and connections. Students are encouraged to discuss how they use one problem to solve the consecutive problems. Pause here and complete the strings. How can one problem help you solve another one? We can use strings involving both operations to press big ideas about place value. When adding multiples of 10, we could make connections by focusing on the changes in the digit's value. When multiplying by a multiple of 10, we focus on powers of 10 idea and increasing places in a number. If students need support with making connections between the problems, visual models are a great way to help them see what is changing and why it's changing. As our students start to figure out that pattern of multiplying by tens, we'll often hear them say, oh, well, you're just going to add a zero. For example, 12 times 10, they think of as 12 plus 0. Using precise language is a part of our math practices, so push for them to notice that really the number increased by a power of 10. The number's place value increased by 10. And this understanding is critical as we start moving to working with decimals. A common misconception in later years is that we'll see students compute 1 and 2 tenths times 10 as 1 and 20 hundredths, adding a 0. It always worked with whole numbers, but this faulty reasoning will break down when operating with decimals. By the end of first grade, our students are expected to understand that the two digits of a two-digit number represent the amounts of tens and ones. And then in second grade, they extend their understanding to three-digit numbers and the meaning of the digits in the hundreds, tens, and ones place. So first and second graders are generally familiar with numbers up to 100. Many of them can write the numbers from 1 to 100, and many can even compare numbers, for example, 54 and 45, and tell which is greater. Many can identify which digit in two-digit numbers is in the tens place and which is in the ones place. And I think we've all seen these types of assessments that check students' understanding of place value. So here's a worksheet where students fill in missing numbers, circle the greater numbers, and indicate whether digits are in the tens or ones place. But if we pause to ask students questions face to face, sometimes their responses are surprising and give us disturbing evidence of shaky understanding. For example, while students could fill in missing numbers correctly, when asked to count to 100, some students are confused when changing from one decade to the next. For example, stumbling when they reach the number 29 and not sure what would come next. When asking students to write a number like 38, some incorrectly would write 308, writing 30 as they said 30, and then writing 8 as they said 8. While they could tell which digit was in the tens place and which digit was in the ones place, when comparing 54 and 45, for example, some would only offer the explanation that 54 is greater because it comes after 45. Their explanations don't relate to the place values of the digits. Rather than a paper pencil assessment, let's consider a student interview. We want the interview to be short because the information is important to get from everyone in the class. We also want the interview to be efficient, where it requires just a minimum of materials. And thirdly, we want the interview to be informative. We want it to give us clear information about students' understanding. So watch these videos of Anna, Daryl, and Jonathan as they are interviewed for some place value understandings. Anna, after she asked for the question to be repeated, she responded automatically that the 1 in the number 16 meant 10. Daryl responds correctly, counting out the remaining cubes to show that the 1 in the number means 10. And then Jonathan also demonstrates his understanding of the meaning of the digits. However, other students' responses indicated their lack of understanding. Pause here to watch Gabriella and Dennis. And then later on, you might want to try this assessment with your students. Maybe first predict what individual students will say and do, and then ask and see what you learn. So now let's take a moment to connect to the standards for mathematical practice. Here's some questions to help us think about the information that's been presented in this module and how it connects to the practices. If we had to pick two practices that stood out as the focus, which ones would you pick? Why? Go ahead and jot down your ideas.